Ladies and gentlemen, after the first talks of the day, we have learned a lot of broken things, and now we have a talk with a title promising to do something better, improving the security of session management in web applications. Yeah, Philip is from the University of Leuven and is part of a research group, and I think Philip will introduce himself and his group. Okay.
Yeah, okay, thank you. Good afternoon, everyone. I'm Philip from the University of Leuven, as he said. I'm part of the DistroNet research group, and I'm a PhD student, currently in my fourth year, so I'm nearing the end. And my research is focused on several things, and one of these is web application security and more specifically session management. So, as you probably all know, session management is used in web applications to tie multiple requests together, because HTTP is basically a stateless protocol, which means that as a server, there's no real way to tie multiple requests together. So if you receive two requests, you don't know whether they belong to the same user, whether they come from different machines. So basically they invented a mechanism called session management, which allows you to tie them together as a single session. It also allows you to store data at the server, so you can keep some information in the session, like the authentication status. Is user authenticated? Who is this user? And sessions are typically identified by some kind of token, a session identifier. So this session identifier is included in every request. So you probably all know the session cookies. It can also be as a parameter in the request. And it allows the server to look up the correct state. Important here is that this session identifier is actually a bearer token, and that means that the one who presents the token is assumed to be in control of that token and the accompanying session. So two examples. The first one is very well known, or should be very well known. It's basically a session cookie, which is set by the server, which contains some unique random value, and is sent by the browser on every request to the same domain. So whenever a server receives that request, he knows, okay, this belongs to that session with this and this state, so I can process it accordingly. As a fallback mechanism, it can also be done as a parameter. So basically you have a URL, and in the URL you have a parameter with the session ID embedded. This means that the application would have to rewrite every URL. It also means that it can easily leak. For instance, in the referrer header, it can leak out. It can be stored in log files, things like that. So it's not a preferred mechanism, but a lot of applications and frameworks still support it as a fallback in case cookies are not accepted. So it's important to consider. The problem here is that these things are actually flawed by design, and it's mainly the bearer token that forms the problem. So it works fine as long as you assume that the token cannot leave the browser or the server, but once an attacker gets control of the bearer token, he also controls the session. So because of the bearer token characteristics, once an attacker presents it to the server just assumes, okay, this is user Philip because the session belongs to him, so I'll process this request in his session and transfer some money from his account or send a mail in his name or whatever. And especially with session identifiers, they are very popular. It's one of the most popular cross-site scripting attacks. These kind of attacks are also number 2 in OWASP top 10, so everything to do with broken authentication, session management. It's very prevalent, it's very dangerous, and there are numerous attacks that specifically target this thing. So I'll illustrate two in the presentation here. You have session hijacking and session fixation. I'll explain briefly what they do and how they work. So in a session hijacking attack, an attacker basically will take over the user's session. He will get full control, and this is especially problematic after authentication, because the user once authenticated and the session is transferred, then the attacker has access to a fully authenticated session. There are two very common attack vectors. One is from JavaScript, so by injecting a script and extracting the session identifier, the attacker gains control of the session, and the other one is by eavesdropping on the network. Common example here is Firesheep, which you probably heard of. In case you haven't, you should look it up. It's a Firefox add-on that allows any wireless network user, just by point and click, to take over Facebook sessions, Google Plus sessions, anything that is transmitted in the clear. So how does it work? Very schematically, you have a victim which will connect to a target server, and you have the attacker here. So basically what happens with any web application, basically, you connect, you get some page from the server, which includes a session identifier, in this case, for instance, a cookie. You authenticate to the application. You use the session identifier to establish an authenticated session. And then the attacker is able to steal your session identifier. For instance, he's on the same network, he sees it flying by in clear text, so he just grabs it out of the air. You don't even have a clue that that happened. Once the attacker now connects to a target application using the session identifier, he basically is greeted with your session, and he can do whatever you are allowed to do in your session. Second attack is session fixation, which is lesser known than session hijacking, but nonetheless also very dangerous. And what you do here is actually you reverse the process, and you will force the user to work with your session as an attacker. So this can also be done through JavaScript, meta tag injection from a related domain if you have multiple subsites, or even with by sending a simple URL to the user containing a session ID. So again, schematically, how does it work? In this case, the attacker will first establish a session with the target application. So he just acts as a normal user, he gets a session with a session identifier, and he stores it in a browser. Then he transfers this session identifier to the user's browser. So with a very simple example, if you have parameter-based session management, you send him a mail with a link, like here's a funny video of a cat, question mark, PIP session ID is 123. The user clicks on this link, okay, who wants to see cats? Everybody apparently on the internet. So he opens this link, sends the session identifier to the target application, which then could ask the user to authenticate himself. When this happens, it happens within this session, which is actually the attacker session. So the user successfully authenticates, everything looks fine. But once the attacker detects the user has authenticated himself, he can take over the session once again. So this is very similar to session hijacking, and in both cases, the attacker ends up with an authenticated session under the user's name. So what can we do to protect against this? Of course, these attacks have been known for quite a while. There's extensive research on it, and there are things you can do. Even OWASP has a nice document listing most of them. First of all, general advice for session management, you need to choose strong, unique session identifiers. Of course, if you don't, an attacker can simply brute force it. There's no need for hijacking, fixation, or whatever. So if you have good, strong values, that's step one. The second step is to rotate them after you change your privileges in the application. So for instance, after an authentication, rotate the session identifier, switch it to something else. So in case the attacker already had it from before, for instance in a session fixation attack, it's useless because it has changed after the authentication and he can no longer access the authenticated session. Of course, if you have a session hijacking after authentication, you're still vulnerable. And the third piece of advice is to deploy your site over HTTPS. This should take care of some eavesdropping attacks, but these by themselves are not enough. So for cookie-based session management, there are some additional steps you have to take. Forget one of these and you still remain vulnerable to several session management attacks. First of all, the HTTP-only flag, which is probably well known, should be enabled for session cookies because it basically prevents any JavaScript from reading or writing to these cookies. So this would prevent a cross-site scripting-based session hijacking attack, for instance. You have the secure flag, which should be enabled on HTTPS sites because it prevents the session cookie from being sent on an HTTP channel. So if you don't do this and even your whole site is HTTPS, there are still attacks like SSL stripping or things like that can be used to obtain a session cookie. So also use that flag. And it's always useful to limit the lifetime of a session cookie. So even if there might be some attack, it's still limited in time and not valid like forever. So it seems like the problem is solved, but unfortunately it isn't, otherwise I wouldn't be here today. So the problem with these cases is that, first of all, they're not deployed that often. So they have been around for a few years. HTTP only is even quite old. But even nowadays, sites don't deploy this. So they remain vulnerable for this kind of attacks. While HTTP only is fairly easy to deploy, frameworks can enable it by default because a session identifier is basically useless in JavaScript. You don't need it there. So enable it by default and you offer some protection. I think this year the new Tomcat came out and they have it on by default now, so things are starting to move, but still globally on the internet it's a very depressing situation. Same thing for secure. If you have an HTTPS site, you should have secure cookies, unless they're shared over HTTP, which is problematic, but then you cannot use it because you need them on HTTP. A second thing is that the HTTPS deployments are fairly limited. If you look at any website on the internet, they typically protect the sensitive part, like the authentication process, because there are credentials there. We need to protect this. But then they switch right back to HTTP using the same session identifier over an HTTP channel, which is exactly the case that Firesheep is making. Like, don't do this, it's really problematic. With 3 clicks, your session is stolen and taken over, but websites keep doing it. I don't know, honestly, I don't know why. There are many reasons probably for the lack of HTTPS deployment. I can speculate about some of them. Maybe you have an insight why your corporation doesn't do it or why you do it. Please come and tell me, I'm very interested to know. But some of the guesses I can make is developers generally don't know. Maybe it's valid for the smaller websites. They don't care, it's also possible. The whole certificate mess is too complex or too expensive, might be a reason. People with a lot of boxes in between, like caches, intrusion detection, load balancing, might find it too complicated or impossible to have SSL enabled because it interacts with these kind of services. Or some applications might just not need it. So if you have, for instance, a blog which has all public information, you've outsourced your authentication process to an identity provider like OpenID or Google or whatever. You're like, okay, I have no sensitive information, I don't need SSL at all, because what do I care? Unless, of course, your session management remains vulnerable, and that's exactly what we see happening. So the problem we're trying to address in our work is you have HTTP applications which basically have no protection. They're just out there on the web, plain text. Anybody in the neighborhood of a user can eavesdrop on the traffic. And if there's a vulnerability, you can easily take over the session. On the other hand, you have HTTPS applications, which are fairly secure. The HTTP-only and secure attributes on the cookies, combined with something like a strict transportation header, provides adequate protection. It's not perfect, but it's acceptable. So I would be really happy if all sites do this. But in between, you have like this huge gap where there's no real solution. So what we are trying to do is to improve the session management of HTTP applications so that they gain the advantages offered by these attributes. So ideally, we would have HTTP applications with secure session management, and if they decide that they want further security properties like entity authentication or confidentiality or integrity, the exact items offered by HTTPS, then they can decide to upgrade to the full HTTPS experience with all security properties that are attached to it. But unfortunately, that's not the case today, and hopefully we can make a difference in the coming years. So the example I will use to explain our technique has to do with third-party authentication. So I'm assuming an application like a blog, which has public information, which outsources its authentication to services like OpenID, Facebook, or Google, and actually doesn't really need HTTPS, but wants secure session management. So it's actually, I think it's a good thing that you have these services because they're specialized in doing authentication. They provide 2-factor, 3-factor, whatever factor authentication. They include mobile phones and whatever. So they actually give a good experience. And by offering them to other websites, the websites are able to include safe authentication processes without doing all the work themselves. So to illustrate how this would work very schematically, I have a brief sequence diagram. So you have the browser on the left, that's the user. You have the server, that's the application you want to provide, like the blog. And you have an OpenID provider. So what you typically do is you go to the blog website as a user, you send some request, the blog website responds, sets a cookie for session management, which is stored in the browser, and it redirects you to the authentication provider, in this case an OpenID provider. You go there, you get a login page, okay, login page is fetched, and a cookie is set for the OpenID provider because it also needs session management. It's a different cookie, different service, so fairly normal. You authenticate as a user with credentials or whatever. In this case, it's opened up to the provider to take care of this. You submit your cookie because it's within your session, and you get back some kind of authentication assertion or token or whatever, depending on the service. This thing is then sent to the server where you wanted to authenticate to, which can validate this token from the OpenID provider, saying, okay, this is signed by the provider, it looks good. And it says you're authenticated as user Philip. So I will link this to your account here. And you also, of course, send a cookie so it can take care of session management where necessary. So I will now present our improvement to session management, and then I will revisit this example to show how this works. So what we propose is to provide secure session management with some additional properties. So what we want to ensure is that once you establish a session between two parties, that the session remains between those two parties. So it's not possible to transfer it to an attacker computer, for instance. So unless you give explicit permission, which I won't go further into. So if we have this, if we have a session that remains between the initiators, you effectively disable eavesdropping attacks and also in-application attacks like cross-site scripting attack or something like that. Additionally, we would like this thing to work with third-party authentication scenarios, because there are solutions that do this, but they typically are incompatible with third-party authentication scenarios, so they might not be useful in the web, which outsources these things. So, on a high-level overview, what we do is we establish a shared secret. We use a variant of the Diffie-Hellman key establishment algorithm. I'm not going into the crypto details. You can find it in the paper if you want to. We introduce a new session header, which basically contains a session identifier, which can be publicly known because it's useless without the secret stored in the browser used to generate signatures. So what basically will happen is the server will receive a request, know the session, and then if he can verify the signature that belongs to that user, which is stored in the session, only then he accepts the request, otherwise he rejects it. And the secret is locked in the browser. It's not accessible to any API. It's not transmitted over the network. So basically, it's unreachable to an attacker unless he controls the user machine or things like that, which we consider out of scope. So on a very high level, how does it work? You have a browser and you have a server here. So in the first request, you simply contact the application and you ask for some resource. You indicate that you support this new session management mechanism so that the server knows it can use this instead of the old cookie system or whatever. Server responds with the resource you requested and gives you a session identifier. Then some hocus pocus happens to establish a shared secret, which I will talk about in a moment. And once this is done, the browser can send a second request with this session identifier and some signature. So the server can verify this signature because they have a shared secret and see whether this is actually a valid request or not. And if it is a valid request, it responds. If it isn't a valid request, it can assume that an attacker is using this session identifier with a different shared secret because the signature doesn't match, and it just discards the request. So, yeah. Okay, so the signature is based not on, well, it includes the session ID. The exact parameters, we haven't defined them because it's up to how much integrity you want. But what you need to include, it will be more clear on the next slide, but you need to include the session identifier and some counter to prevent replay attacks. And you might even want to include the data to prevent manipulation attacks on the network level. So, that was a high-level overview. In a bit more detail about establishing the shared secret. What actually happens in the beginning is the browser generates a key, K, and calculates the HMAC for the first request and sends it out. So at this moment, only the browser knows the key. It sends the support header like I support sessions. Here's some counter to prevent replay, and an HMAC of this first request. The HMAC is calculated using the key K, so it's based on the shared secret, which is not yet shared. The server, at this point, he cannot verify the signature because he doesn't have the key. But what he does is he stores this for later, generates a new session identifier for the new session object, and generates a public part for the key exchange, which is some detail about the cryptographic algorithm, but it's not important to know what it's for. Just he generates it and he submits this public part to the client. This can be observed by an attacker on a network. It's fine because it's one of the properties provided by the algorithm. So at this point, the client has his response and his session identifier. He calculates a second public part to send to the server, which will allow the server to calculate the key. Again, he HMACs his request and sends it out. So what you have here is a session identifier, which is given by the server. You have the public part, which combined with this can be used by the server to calculate this key, but not an attacker. And you have again a counter and an HMAC. So the server at this point verifies whether this is correct. He calculates the key and now can verify both HMACs, and if they actually match the request, then he is sure this is sent by the user. If one of these is a mismatch, then the attacker is trying to get in between and he can abort the whole situation. Once the key, once this checks out, he stores the key, and with this key he can verify any future request which has an HMAC based on that key. So he just responds, server is done with his tasks except for verifying, and the client in the future just sends the session identifier, a counter and an HMAC. So as promised, I will apply this to the running example I introduced before. So in the first request to the server, the client indicates like, okay, I support this new session management mechanism, some counter, some HMAC. He gets the redirect. He gets a session identifier between browser and server and some public value. Then he goes to the OpenID provider. He does not have a session, so he generates a new key, sends a new support header, gets a new identifier and a new public value. He submits his credentials in the next step, where he submits the second public value. So the OpenID provider can now calculate his key for his session between the browser and himself. And if authentication is successful, he provides the client with the right assertion to relay to the target server. So here it's actually the same story. You have the session identifier from here, you have a public part that belongs to this public part, and this should be 2, and you have an HMAC. So basically after this you have established an authenticated session using the assertion and the new session management technique. One important thing here, this transaction between the OpenID provider and the browser submits credentials, so you should do it over a secure channel. It doesn't change, and it probably will never change in the whole history of the web. As long as you submit sensitive information, do it in a safe way. But this transaction between the browser and the server can happen over a plain text channel, so no longer encryption is no longer needed, because there's no sensitive data that can leak out, and the shared secret is only stored in the browser and the server, so never transmitted, so there's nothing to be stolen. Of course, you have to watch out that this assertion does not become a bearer token, because otherwise an attacker can still use it to hijack or fixate sessions. But that's something up to the specification of the authentication provider. So OpenID specifically mentions this and takes care of it. If I remember correctly, OAuth doesn't provide it, so it's one of the known vulnerabilities and something that needs to be addressed there. Okay. To deploy this, of course, it's a change to the web platform, so it's not easy to deploy something like this. What do we need to improve session management or the security of session management? We need the session header to be supported. At the server side, you could implement this as a session management mechanism in your framework. So for instance, in PHP, what you typically do is you do session start, and then the session management mechanism kicks in, which is cookie-based. Here, you could replace it or augment it with the session header. So it's actually transparent to the application, but the framework takes care of it. At the browser side, things are a bit more difficult. You have to implement support for the session header, which you can do either directly, but then you need to convince Mozilla or Chrome to do it. You could do it as an extension for a select number of users, but the problem there is, since you have to sign parts of the HTTP request, you need to be sure that you're in the end of the line of extensions handling the request, otherwise the HMAC might be violated and might not be correct. An important property is, since we work on the header level and add a new header, we can still use cookie-based session management as a fallback. So if a web server doesn't support the session mechanism, the session header, he just sends back a cookie header, and the browser, which still supports cookies, can still use the cookie-based session management. So we don't break any existing things. Also, for legacy applications where you don't want to update the code or simply not able to update the code, which is basically half of the internet, you can use a server-side proxy that translates between cookie-based session management and the session header. So since this all happens at the server side, the dangerous part, where the data is transmitted, is replaced by the new session management mechanism, and the old part, well, the internal server-side part still uses cookies, which are never exposed. So that's a good option for legacy applications. Two other scenarios where this, well, we have seen the third-party authentication provider scenario, but two other scenarios where this is really useful. The first one is the combination of HTTP and HTTPS. So this is actually very common on the web. I've investigated a few sites how they deal with this, and many sites actually fail to provide this in a secure way. So the problem here is if you switch to HTTPS and then switch back to HTTP, your bearer token, which is your cookie for session management, becomes vulnerable. In the case of secure session management, it does not become vulnerable because it's locked in the browser. So this is actually a good solution. Many sites suffer from this. I told you I investigated a few sites. To give some examples, Amazon does it quite well. They have a cookie for the HTTP part, a cookie for the HTTPS part. So the HTTP part is the shopping itself, browsing products, adding things to the cart. That can be hijacked. But whenever you switch to a sensitive operation like checking out or whatever, it switches to HTTPS and it requires the HTTPS cookie to be there. And if it's not there, so if you hijack the session, it's no longer there, Amazon kicks you out and you have to re-authenticate. So they offer adequate protection. Facebook, on the other hand, does not, unless you opt in for HTTPS, which is very optional and not many people use it. They also have HTTP and HTTPS cookies, but if you go to a sensitive operation without an HTTPS cookie, they happily comply. So they don't take care of this. I don't know whether it's a bug or intentional. I didn't further investigate it. A second scenario are HTTP-only applications. Of course, they are really vulnerable because they submit authentication information like credentials over plain text. You would think like, who does this? But I've seen it, so it happens. So the problem here is we can protect their session management, but as long as you transmit your credentials over plain text connection, then an eavesdropper can still gain access. Additionally, if you have only HTTP applications, it's very difficult to protect against active network attackers because they can do a man-in-the-middle attack. And if you're a man-in-the-middle, you can simply act as a server, accept everything, and pass it along. And you're actually sitting in the middle, which is exactly the problem that's solved by a TLS, which has entity authentication with the whole certificate management and PKI infrastructure that effectively protects against this kind of attack. We opted not to support this because what you're then doing is basically reinventing TLS, which is of course a lot of wasted effort. So if you deploy secure session management and you want additional protection like entity authentication and confidentiality and integrity, you should deploy TLS in one mode or another in combination. Okay. Then I have some related work which has done in academia around this topic. So first one is session lock. I'll go over it very quickly just to give you an idea of what else exists and what properties they have. So session lock basically works with a secret in the browser. It's stored in JavaScript, so it's very insecure against cross-site scripting attacks, for instance. It uses AJAX to rewrite every request and include a secret token. And the paper itself states that it works well with simple applications, but once you have a very complex AJAX application, things become really difficult and it's hard to support it. A second option is the HTTP integrity header. So they try to provide integrity on HTTP, which would include protection for the cookie, the session cookie as well. They use a secret key fetched over TLS or with traditional Diffie-Hellman, and the main problem here is that it takes a while if you have the non-TLS option before you can start protecting the integrity. So you have to go back and forth to establish a shared secret, and only then you can protect the resources. A third one is BetterAuth, which is done by Martin Jons, who's one of the organizers here. It's actually a good solution that offers protection. It's based on a key agreement which uses the user's password to establish a shared key. The password is considered to be a shared secret, so the server knows it, the user knows it. So based on the user password, once you enter it, the browser generates a key and uses that for authentication instead of the password itself. So the password never transfers over the wire. Unfortunately, since it depends on the password, it's incompatible, in its current form at least, it's incompatible with third-party authentication. And it depends on HTTPS for the initial setup, because you have to get the password at the server side, of course. And then the final one is TLS origin-bound certificates, which is actually an extension to TLS. I believe it's being implemented in browsers under the name Channel ID. And what they basically do there is they automatically generate client certificates which are used in the TLS connection. So they get strong authentication properties. And they also support the binding of tokens to the channel. So you can bind your session cookie to the channel, and because of the strong authentication properties, you can guarantee that an attacker is not able to transfer the channel somewhere else, so we cannot transfer the tokens as well. So to conclude, in this talk I have presented our proposal for secure session management. Maybe it's not perfect, so if you have input on that, I will be glad to hear it. But inherently, we try to fix the problem with session management, which lies in the bearer token. So if you remove the bearer token from session management and replace it with something else, you automatically gain the properties you actually expect from a session management mechanism. Our mechanism is compatible with third-party authentication providers, which is an important use case in the web today. And it's compatible with legacy applications or browsers that don't support it. I hope you enjoyed the talk, and if you have any questions, I'll be glad to answer them now, or anytime later. You can grab me here or send me an email if you want to.
Philip, thank you very much. Are there any questions? Dave.
Would you implement the client-side pieces of this in JavaScript?
Can you repeat?
Okay. So the question was if you could implement this as at the client side using JavaScript. That's actually a very good question. If you possess the right cryptographic APIs to make signatures, I guess you could make a prototype using the XHR object to show that it works. Yes. Yeah, that's true. Of course, you cannot have protection against cross-site scripting attackers, but as a prototype, yes, that would work, I guess.
Further questions? So the question is why we used Diffie-Hellman instead of automatically generating public-private keys. It's actually, again, a good question. I think the problem there would be if you generate a public-private key, how you know or how you transfer the keys, right? Yeah, that's something to check out, whether that would be feasible or not. No, indeed, it's an option to check out. Thanks. And I have a question. What about cross-site request forgery attacks against session management?
Excuse me, can you repeat?
What about cross-site request forgery attacks on the session management?
Yeah. That's actually a whole other problem, because cross-site request forgery attacks don't steal the session identifier. They just use the browser's feature that if you send a cross-domain request, that it adds authentication information, which is needed for Facebook Connect or any other cross-domain functionality. Honestly, I don't think session management can protect against that, because the core of the problem is that you lack the user's intent of making a request. You don't know whether the browser makes it and it's intentional, or whether an attacker injected it and it's an unintentional request. So you would have go to a situation where we restrict the access paths within an application and can say that only through the right paths you can make a request. But I doubt that it's a thing that can be fixed from within session management. But
yes, I think so. You have add additional security countermeasures against cross-site request forgery. Yeah. Okay. Another question? Yeah.
Okay, so the question is why don't web server creators or producers use HTTP only more often? Browser creators. Yeah, okay, so the correct question was why browser vendors don't set the session cookies HTTP only by default, and how many sites would break. Actually, we did some research on that. Well, my colleague there, Nick, did Session Shield, which is a client-side proxy that does exactly that. And he used some heuristics to determine which cookies are session cookies and which are not. And I did that as in combination with session fixation in a browser add-on called Serene. So if you know which cookies are session cookies, then you could do it. So I doubt that many sites would break, but the problem is that next to the predefined session cookies like PHP Session ID, there are a lot of sites that use custom cookies, with Facebook as a prime example, for instance. And using heuristics to determine the correct cookie is fairly difficult. You can do it up to some level, and then you have to start guessing, and then things start breaking. So I guess you could do it for about 95% of the sites. But why they don't? Well, browser vendors really don't like to break things. So
one example are Java plugins. Okay. Okay, thank you very much for your attention, and thank you, Philip, for your talk. Ladies and gentlemen, after the first talks of the day, we have learned a lot of broken things, and now we have a talk with a title promising to do something better, improving the security of session management in web applications. Yeah, Philip is from the University of Leuven and is part of a research group, and I think Philip will introduce himself and his group. Okay.
Yeah, okay,
thank you.
Good afternoon, everyone. I'm Philip from the University of Leuven, as he said. I'm part of the Disnet research group, and I'm a PhD student, typically identified by some kind of token, a session identifier. So this session identifier is included in every request. So you probably all know the session cookies. It can also be as a parameter in the request. And it allows the server to look up the correct state. Important here is that the session identifier is actually a bearer token, and that means that the one who presents the token is assumed to be in control of that token and the accompanying session. So two examples. The first one is very well known, or should be very well known. It's basically a session cookie which is set by the server, which contains some unique random value and is sent by the browser on every request to the same domain. So whenever a server receives that request, he knows, okay, this belongs to that session with this in this state, so I can process it accordingly. As a fallback mechanism, it can also be done as a parameter. So basically you have a URL, and in the URL you have a parameter with the session ID embedded. This means that the application would have to rewrite every URL. It also means that it can easily leak. For instance, in the referrer header, it can leak out. It can be stored in log files, things like that. So it's not a preferred mechanism, but a lot of applications and frameworks still support it as a fallback in case cookies are not accepted. So it's important to consider. The problem here is that these things are actually flawed by design, and it's mainly the bearer token that forms the problem. So it works fine as long as you assume that the token cannot leave the browser or the server, but once an attacker gets control of the bearer token, he also controls the session. So because of the bearer token characteristics, once an attacker presents it to the server just assumes, okay, this is user Philip because the session belongs to him, so I'll process this request in his session and transfer some money from his account or send a mail in his name or whatever. And especially with session identifiers, they are very popular. It's one of the most popular cross-site scripting attacks. These kind of attacks are also number 2 in OWASP top 10. So everything to do with broken authentication, session management. It's very prevalent, it's very dangerous, and there are numerous attacks that specifically target this thing. So I'll illustrate 2 in the presentation here. You have session hijacking and session fixation. I'll explain briefly what they do and how they work. So in a session hijacking attack, an attacker basically currently in my 4th year, so I'm nearing the end. And my research is focused on several things, and one of these is web application security and more specifically session management. So, as you probably all know, session management is used in web applications to tie multiple requests together, because HTTP is basically a stateless protocol, which means that as a server, there's no real way to tie multiple requests together. So if you receive 2 requests, you don't know whether they belong to the same user, whether they come from different machines. So, basically, they invented a mechanism called session management, which allows you to tie them together as a single session. It also allows you to store data at a server, so you can keep some information in the session, like the authentication status. Is user authenticated? Who is this user? And sessions are